continuous functions on the unit interval. So we're going to work in the space C of 0, 1, continuous functions on the unit interval. And first of all, we have to note that this is complete. So step 1 is that C of 0, 1 is a complete metric space. So if we take a Cauchy sequence, so we consider a Cauchy sequence Fn in C of 0, 1, then at any particular point, at any x, the absolute value Fn of x minus Fm of x is certainly at most the supremum of the difference, and consequently the sequence of functions is at least pointwise Cauchy. So what you get is that the sequence of real numbers Fnx is Cauchy for each x. And that means you can take a pointwise limit of the functions. So Fn of x converges to some function f of x at each point x. So given epsilon greater than 0, there exists a capital N such that the infinity norm of Fn minus Fm is less than epsilon for all m and n greater than or equal to capital N.
Just a small question, like by the infinity norm of Fn minus Fm, you mean the supremum of that function over there?
Yes,
okay.
the supremum of the absolute value of Fn minus Fm.
Okay.
Right, so if that's true, then we have the absolute value of Fn of x minus Fm of x less than epsilon for all x and all m and n greater than or equal to capital N. So letting n or m go to infinity, we get the absolute value Fn of x minus f of x less than or equal to epsilon for all x and for all n greater than or equal to capital N.
Less than or equal to epsilon?
Sorry?
Why is it less than or equal to epsilon?
Okay, in the limit, even when we have strict inequality of numbers, xn is, say, less than 1. When I proceed to the limit, it could change into less than or equal to. It's like the numbers 1 minus 1 over n are strictly less than 1, but when you go to the limit, you get 1. Okay, so we have uniform convergence. We have convergence in the infinity norm of the sequence fn to f, and we just have to make sure that f is a continuous function.
I have a quick question.
Yeah.
Just because we know that fn of x minus fm of x is less than epsilon for each m greater than or equal to n, I don't quite understand how knowing that fact allows us to conclude that the inequality there is less than or equal to epsilon as m goes to infinity. It's not clear to me that in the limit you would necessarily have to satisfy that inequality, even with the additional equality statement.
Okay, so for a fixed m and a fixed x, just think of this as a sequence of numbers indexed by m.
Okay.
They're all less than epsilon. When I let m go to infinity, they converge to this number. So if you have a sequence that's bounded in absolute value by epsilon, the limit stays bounded by epsilon. So that's what we're using here.
And then the equality is in the case where the bound may be the least upper bound, or this is the greatest.
Yes, you could end up with equality there.
Thank you.
Okay, so this is saying that the fn's converge to f in the infinity metric. So fn minus f infinity goes to 0 as n goes to infinity. Now we just have to make sure that we're still in the space, so we need f to be continuous. So we check continuity. At some arbitrary point, say A. But x be a nearby point, and I want to show that f of a minus f of x is small in some appropriate way. So we want to look at the difference between f of a and f of x. And I'll write it this way. It's going to be I have to make use of the continuity of the fn's. So I'll write it f of a minus fn of a plus fn of a minus fn of x plus fn of x minus f of x. So I've added and subtracted two terms in the middle there. And so this is less than or equal to absolute value f of a minus fn of a plus fn of a minus fn of x plus fn of x minus f of x. And I want the whole thing to come out less than epsilon. So this would be true if all of them were less than epsilon over 3. Because I have 3 terms. So the way to get that is to argue as follows. first choose n so that the infinity norm of f minus fn is less than epsilon over 3. That will take care of the first and last terms without even knowing what a and x are. To take care of the middle term, we use the continuity of fn. So there exists a delta greater than 0 so that the absolute value fn of a minus fn of x is less than epsilon over 3 when the absolute value of a minus x is less than delta. So there we've used the continuity of the function fn. So therefore, if a minus x in absolute value is less than delta, what we get out of the inequality on the right-hand board is that the absolute value f of a minus f of x is less than, first term is epsilon over 3, second term is epsilon over 3, and the third term is epsilon over 3, and that's equal to epsilon. And so we've satisfied the definition of continuity for the function f at an arbitrary point a. And therefore, f is continuous and so the continuous functions on the unit interval form a complete metric space. So with that out of the way, once we're in a complete metric space, we can hope to apply Bayes' theorem. So let's have a look at what it means to have just a right-hand derivative at a point. That's certainly a minimal requirement for having a derivative. Step 2 is, what can we conclude if a function f of x has a right-hand derivative at a point A. Now, in order to talk about right-hand derivatives, you have to be able to take a limit from the right. So it doesn't make sense to talk about point A being 1. So this will only make sense if we're in the half-open interval 0 to 1. So let's write down the definition. Given epsilon greater than 0, there exists a delta greater than 0, so that when you look at the difference quotient f of x plus h minus f of x divided by h, well, as h goes to 0 from the right, that should be tending to the right-hand derivative. So this should be less than epsilon for 0 less than h less than delta.
Should be f of a plus h,
Should it be what? Sorry?
f a.
Oh, yes, thank you. We're looking at the point A. So this implies that the absolute value, f of a plus h minus f of a over h, should be less than f prime of a plus epsilon. And that is for 0 less than h less than delta. So we can conclude that the difference quotient here in absolute value is bounded by some constant. Now that's supposed to be true for all epsilon, so you could take here epsilon to be 1. Now it's a little cumbersome in the way that we have it formulated there, so I want to change it slightly. So let us now choose n so large that several things happen. First of all, since a is strictly less than 1, a is in the interval from 0 to 1 minus 1 over n. That's certainly possible, since 1 minus 1 over n tends to 1, it will eventually get to the right of a. Also, 1 over n should be less than delta. I can certainly achieve that by taking n large enough. And thirdly, that constant on the right, f prime of a plus 1, n should be at least f prime at a, the right-hand derivative, plus 1 in absolute value. So there's an absolute value missing here. So I only have 3 things to do, and each one is true when n is large enough, and therefore I can find one sufficiently large value of n that makes all 3 of these true simultaneously. And so what does that say over there? So we get the following statement. The absolute value f of a plus h minus f of a divided by h, I'm going to put a less than or equal to. Certainly if it were less than, then it's also true that it's less than or equal to n. And now, since 1 over n is less than delta, this is true for all h between 0 and delta. So in particular, it's true for h's between 0 and 1 over n. So the point of this reformulation is to get rid of the epsilons and deltas and the f prime of a and just reformulate it in terms of a particular integer n. So if, just to recap, if we have a right-hand derivative at some point, then for a sufficiently large choice of n, what I have written there will be true. And so this is a minimal requirement for the right-hand derivative at A to exist, because it's a consequence of the existence of the right-hand derivative. So what we're going to do is take that condition and use it to define subsets of 0, 1. Or rather, subsets of the continuous functions. So for each n greater or equal to 1, we're going to define a subset of the continuous functions c of 0, 1 as follows. And we have to say what it means for a function to be in this set. So it's the continuous functions f and c of 0, 1 with the following property. There is some point x in the interval from 0 to 1 minus 1 over n, so that the absolute value f of x plus h minus f of x divided by h is less than or equal to n for 0 less than h less than 1 over n. So it looks a bit like differentiable, but it's not, it's weaker than that. Just want that inequality satisfied, just for some, for some point in the interval. We're not even saying it should be true for all x's, just there is an x at which that is true. So I've just taken this condition here and used it to define a set of functions that satisfy this. So from what we've done, each function that has a right-hand derivative at some point a in the half-open interval 0 to 1 is in some en. There's a sufficiently large integer n so that that function is in there. And that's because we showed that this condition is true.
Those are not necessarily disjoint, are they?
No.
Okay.
No. Right, so anything that has a right-hand derivative somewhere ends up in one of these ENs. So if we're looking for a function that has no right-hand derivatives at all, we should look in the intersection of the complements. So the intersection of EN complements consists of functions without right-hand derivatives. right-hand derivatives anywhere. So we just have to show that this is non-empty. So the third step, we're trying to, it's starting to look like Bayes' theorem here. We need the ENs to be closed, then their complements are open. And if their complements are dense, then we will have a countable intersection of open dense sets. And we know from Bayes' theorem that that is still dense. In particular, it cannot be the empty set. And everything in there is going to be a function with no, a continuous function with no right-hand derivatives at all. So the third step is we will show that En is closed. So let's consider a Cauchy sequence. Fk in E sub n. By completeness, we know that there is a continuous function f so that the infinity norm of Fn minus f goes to 0. Of course, what we need is that the limiting function f should also be in En. So let's have a look at what it means to be in En. If the function fk is in En, then there is at least one point where that inequality is satisfied. So each k there is a point xk in the closed interval from 0 to 1 minus 1 over n, so that the absolute value f of xk plus h minus f of xk divided by h is less than or equal to n for all h's between 0 and 1 over n. Now those points xk, they're all living in a closed interval, 0 to 1 minus 1 over n. So the Bolzano-Weierstrass theorem tells us there's a convergent subsequence. Now, so the notation doesn't get out of hand, once we take this subsequence, I'm just going to replace the original sequence by the corresponding f sub k sub r's. And so, by dropping to a subsequence, we could actually assume here that we have a sequence where the xk's converge to something. So, by Bolzano-Weierstrass, a subsequence of the xk's converges some point A in the interval 0 to 1 minus 1 over n. By dropping to the subsequence, we can assume that the original sequence xk converges to A. Now I want to show that, and this should have a subscript k on it, fk. I want to show that the same kind of inequality is true for the function f at the point A. So let's look at a fixed h in the interval 0 to 1 over n. I want to look at the difference between f of a plus h minus f of a. I'm going to forget the h in the denominator for the moment and just work in the numerator. And I'm going to add and subtract terms. So this is going to be f of a plus h, and then I will subtract f of xk plus h. Then I add it back in. Then I subtract off fk of xk plus h. And then let's see, I have to add that back in. And then subtract off fk at xk. Add that back in. This goes on for a while. Let's see. Now I subtract f at xk, add that back in, and finally subtract f of a. Okay, let's just make sure that is correct. These two cancel. These two cancel. These two cancel. And those two cancel. Now, divide by h. And use the triangle inequality. And I have f of a plus h minus f of a divided by h is less than or equal to a sum of 5 similar terms. F of A plus H minus F of xk plus H over H. Then the next one is F of xk plus H minus F k at xk plus H divided by H. So that takes care of that, and that. The next one is Fk of xk plus H minus Fk at xk divided by H. And then Fk at xk minus f of xk divided by H. And finally, the third one is f of xk minus f of A divided by H. So let's have a look at these 5 terms. Well, by the choice of xk, number 3 here is at most n. What about these other ones? Well, f is continuous and the xk's are converging to A, so I'll be able to make this as small as I like with a large choice of k. This one, a large choice of k, will make this as small as I like because the infinity norm of f minus fk is small for large k. That also applies to the 4th term. And then the 5th term will be by continuity of the function f. So now we just have to write down the details. Remember that h is fixed. So given epsilon greater than 0, let us choose k so large that the absolute value f of A plus H minus f of xk plus H is going to be less than epsilon H. Also, absolute value f of xk minus f of A is less than epsilon H. So that's continuity of f at the 2 points A plus H and A. And the infinity norm of f minus fk is less than epsilon H. This gives that the absolute value of f A plus H minus f of A over H, how big can it be? I've arranged it for the first, second, fourth, and fifth terms to be all less than epsilon. And the third term is bounded by n. So this is less than or equal to epsilon plus epsilon plus n plus epsilon plus epsilon, which is n plus 4 epsilon. But this is true for all epsilon greater than 0. Let epsilon go to 0 to get that the absolute value of f of a plus h minus f of a divided by h is less than or equal to n. So this is true for any h in the interval 0 to 1 over n. Remember, at the outset, I fixed a value of h. So h was constant for this calculation. Constant but arbitrary. And that is the defining property for f to be in En. I found a point where this inequality is true. So therefore, f is in En, and En is closed. So that's what we wanted to accomplish in step number 3. So we're just about out of time for today. Let me write down what the next step is. Step 4 is we are going to show that each En complement is dense in C of 0, 1. And that is the last step that we'll need in order to apply Bayes' theorem. Anyway, that will have to wait